Okay, guys, let's get started. 8:30. Yeah, sorry I couldn't be there for the lab yesterday. I hope it was worthwhile. The Dash system that produced that worksheet for the Python 3 tutorial. They were ideally I was trying to get them to come in and do a lecture, but we couldn't work it out at short notice, so that's on me. But I hope at least that was useful. Moving forward, that'll be the assignment time. You guys to go in, you can work on your assignments, you can talk to us TAs, you guys can work together, whatever you want. And then the next week will be the oral examination part of it, as we spoke about it last time. Okay, so linear systems. Now is when things start to get a little bit more interesting. Linear systems are the workhorse of scientific computing. Everything basically comes down to it. And linear systems includes the canonical solve, right? So you have a constant scalar times x is equal to b, and you solve for x, right? Literally all you have to do is divide through, okay? In contrast, x squared or anything where the unknown is anything other than linear is nonlinear. By definition, that's just kind of the catch-all. As it turns out, we can basically use almost always the same techniques to handle nonlinear equations, and they all kind of boil down to linear equations on the inside. I was messing around with this one yesterday. Jupyter Books doesn't like to format normal math as well as the align statements, so you're going to have to use your imagination for now. A more complicated example, and one that we're going to be dealing with a lot, is when you have multiple equations and multiple unknowns, right? So this is ax plus b is equal to, sorry, ax plus by is, it should look like this. By is equal to, what letter do I have there? E, sure, right? And then I've got cx plus dy is equal to, can I use F? Yeah, F, right? Simultaneous set of equations. It is, both equations are linear, therefore the entire system is linear. How familiar are you guys with something like this? Okay, what do you normally do at this point? Matrix, right? So everybody knows, right? At this level, you've got your matrix, and you've got xy is equal to EF. Okay, there are a lot of different ways that we could look at this, though. So let's play around with them and see the pros and cons. Okay, so yeah, we have a set of our unknowns. That's xy in this case, right? We have, what do I say, n unknowns, and we have m equations. How many equations do you need to solve for n unknowns? N, right? You need a square matrix. Is that always true? Ooh, can you have two unknowns and have two equations, but still not be able to solve for them? Anybody? Yes. The fact that the prof's asking the question means, of course, the answer is yes. Rule of thumb, right? In this form, ax is equal to b. We're going to be doing this a whole lot. A is called the coefficient matrix. It is of dimension m by n, right? N is this way, m is this way, m is the number of equations, n is the number of unknowns. X is the variable / unknown vector, right? In general, we like to what's the term? Abstract a lot of our methods to make things simpler. So instead of saying that we have two unknowns, we actually have one unknown, and it is a vector, right? And now we're solving for the unknown vector. Of what dimension is that vector? The computer doesn't care. Because if it knows how to handle a vector, then it can handle whatever it wants, right? A vector with only one element is a scalar. No problem, we can generalize our algorithms. B is the constant vector of this equation. Sometimes it's just called the right-hand vector, right? Which is convenient. And of course, if m is equal to n, then a is square. Okay. Some systems don't have a solution, or they do, but it's not unique. So here's our example. I had a high school summer student come in, and he actually designed this nifty tool. I'll show you guys how to get it, but then we're gonna walk through this part that basically has this guy like kind of instantiated with different plots, make it easy for us to look at. But then I'm gonna show you guys where to get this thing, and you guys can play around with it too. If you go under importable modules down here, I'm trying to get a student in here to help smooth this thing out so that it won't be so janky. But in the meantime, if you go to importable modules, you actually have to go to next, no title, and then you get this guy. Hit the rocket ship, collab. It'll whine that it wasn't made by Google, but that's okay. It's gonna run and it's gonna create this nice guy. And we're going to try and embed this into the website itself so that you guys can just play with the interactive Python thing, right? So this was kind of used to generate those other plots, but for pedagogical reasons, let's go through here. Okay, so that's what this gobbledygook is. Okay, you're organizing a fundraising event. You need to buy chairs and tables, right? Chairs cost 20, tables cost 50. You have a budget of 700. Right? And a total of 20 pieces of furniture need to be bought in total. How many chairs and tables should you buy? Right? This is kind of standard linear algebra, right? So anybody not know how to do this sort of thing? Excellent. Okay, I'm going to go through it anyway. So chairs cost $20. So you say that C is the number of chairs. You say that T is the number of tables. $20 times the number of chairs plus $50 times the number of tables equals your budget, 700, right? But chairs plus tables has to equal 20 because you need 20 pieces of furniture. Okay, anybody? That's good? Good. So the easiest way to do this, and especially with anything with like Colab or anything that you have AI available, just plot it. Because plotting it will tell you probably half of the problem, and if the plot doesn't look like what you think it should look like, then right off the bat, you know that something's amiss. Okay, so that's a big tip. With Colab, this is super easy to plot. Okay, this is what I asked for. Plot the two lines with a grid, right? If you don't know how to plot it, just go open that in Colab, right? And then Gemini is there, and you can literally point it to it and say, plot this equation, and it'll plot those lines. Do you want me to show you guys? Would that be helpful? Yeah? Okay, really quick. Okay, so that's what happens when you hit the rocket ship. You go there. Let's see. So if I just go here, watch this guy. Enter a code block. So you guys at least have some familiarity from yesterday. If not, just follow along. So what I did here was go to this line in between, hit code, and generate with AI. Oh, why does that say empty cell? I don't want that. Well, let's try it. See what it does. Plot the two lines above. Okay, these are just equations. Right? These are just lines, right? You have two variables. You have your constants in there. Two variables in a single equation defines a line. Let's see, right? So here's the code. Just really quickly, because we're in NumPy, we have to define our space, we have to define our axis, and then we evaluate for all these x values what is the y value, right? In this case, the y value is the number of tables, c is the number of chairs. Okay, you plot those two. Matplotlib, Gemini, and AI in general is absolutely fantastic for plotting. I happily need to know very little plot syntax. Any of you guys used Matplotlib before? Like any of these? You know how it's all like, I want the set x limit to be this obscure. Is it square brackets? Is it curly brackets? Is it round brackets? Do you put both into? Do you put that? I don't need to know that anymore. I don't need to know the color codes. You just ask Gemini to do it, and magically, right, you get that. Okay, what's the solution? You got it. Right? Super easy. Jumping back here, 10 tables, 10 chairs is the solution. Okay. How many solutions are possible? Could I have two solutions? Why not? You got it, right? Almost. Because they're two lines, you can only ever have at most one solution or infinite, right? So what I like about the graphical method is that's super obvious. Like as soon as you see this, the line isn't going to curve over. You're not in some hyperdimensional nonsense, anything like that. You can have either one unique solution or all of the solutions. Those are your only two options. Or you could have zero, right? What would this look like if you had zero solutions? We'll see that. It's going to be parallel. Okay. Now, the way that we actually do it, if we actually want to calculate it using our monkey brains, is using elimination, right? Oh, good. Right? So there are different ways to do this. You can substitute. The way that I like to do this is, no. This is not the way that I like to do it personally. This is the way that I've learned how to do it because this fits into Gaussian elimination that we'll talk about on Thursday. Okay, so what you do is you take, just going to write it out just so that we're sure everybody's on the same level here. Okay, we've got 20C plus 50T is equal to 700. C plus T is equal to 20. You multiply this guy, this entire equation by 20, which you can always do. You can always just take an equation and just multiply it directly, right? No problem. Okay, and what you get is 20C plus 20T is equal to 400, right? University math, it's good. This guy minus this guy. The C cancels out by construction. You get 0 plus 30T is equal to 300. T is equal to 10. I can divide. Right? You plug that into any one of these. This guy's going to be your easiest, and you solve your problem. Everybody okay with that way of looking at it, right? You can just as easily do solve C is equal to 20 over T, plug that in here, That gets a little bit more complicated. So if you try and generalize that process to 3x3 matrices, right? 3 equations, 3 unknowns, 100,000 equations and 100,000 unknowns, right? Like that substitution gets clunky. Clunky being the technical term. If you don't believe me, ask Mathematica or like Maple or one of those guys to do it for you. And like all those that cascading fractions and everything, fractions don't simplify very well, right? Unless you have a common denominator, your fractions just kind of accumulate. It gets super clunky, whereas this guy is always neat, right? Because you're just doing that minus that, and you get a simple structure that you can then solve for. And that's what we're going to be doing with Gaussian elimination. Okay. Matrix form. Right? If we write this out into the equation, no big surprise there. We get a standard form, etc., etc. There's our constant matrix. Now, what you guys probably learned to do is to invert the matrix. Is that right? Okay. Turns out you never want to invert a matrix in linear systems numerically. And there are a lot of reasons why. We'll get to that probably by the end of the week. Okay. If you were to do that, though, do you guys remember the equation for, well, it's written right here. If you don't remember the equation for the inverse of a 2x2, it is this, right? The inverse of this guy is 1 over the determinant of your matrix, and then you do one of these swaparoos, right? And if you want to do 3x3, there's an analytic formula, and I think you can actually break that down. I think it is recursive relationship. So you can actually, like the relation or the inverse of a 3x3 is related to recursive applications of 2x2s and up to n. But nobody does it that way. Again, reasons, which we'll get into. Actually, no, because those are the realm of like analytic real functions. And apparently real functions are terrible, by the way. Stick to imaginary functions. Who remembers what the determinant is? Yep, that is the formula for it. Who, from this corner back here, remembers what it is graphically, geometrically. I'm going to start pointing. White hat. It's not the slope. Nobody? Anybody? Bonus points? Anybody for the steal? Yes. Yes. It is the, if you look at that, if you look at those lines, right, and here's where things start to get a little bit funny, right? Our lines went like that. The matrix, if you reduce it, and it's actually been a long time since I did linear algebra, so you're going to have to forgive me. What you do is you get your normal vectors. You get your unit normals, right, for these lines, and that's going to be something that looks like that, something that looks like that, and then the determinant turns out to be the area of this guy. Okay, that turns out to be your determinant. What your determinant means. There's a good technical definition for it. It's the area / volume enclosed by the unit norm or the unit vectors, something like that. We're going to see why that's important in a couple minutes. Okay, so we do that. In this particular case, the determinant turns out to be -30. -30 for an area just means one of those axes are swapped. There's no magic of negative area or anything, right? And then we get our answer and we get that. No problem. Okay. So there's now a discount on the table. Is that clear to everybody? Everybody knows how to do that? Good. There's a discount. Instead of tables are now only $20, right? And the customer slashed your budget down to 400. Sorry. Okay. Who sees where this is going? I mean, the title is right here, so yeah. Okay. So you go like that. Again, plot it. What you're going to find when you plot is this guy, right? This, of course, means, pardon me, infinite solutions, right? For every number of chairs and every number of tables, no, for every number of chairs, there is a number of tables that will satisfy your constraints. So if we had, say, one chair, right? That would mean we would need 19 tables, right? 20 times 1 plus 19 times 20 is 400, right? Similarly, 0 chairs or 20 chairs, right? What about -500 million chairs? Would we get a number of tables that would satisfy that? Yes, we would. Is it meaningful? No, right? We'll just put a pin in that one. That's in the numerical. That's my poetic license for this course. Okay. What does this mean for this guy? What does this mean for the determinant? You already answered. Exactly, right? And this turns out to be a big problem. So if we were to do elimination, right, it's pretty easy to see that we're just going to get 0 = 0, right? In which case the, right, we're going to have a solution for all of them. If we look at this, the actual calculating the inverse, if we look at calculating the determinant, it's going to be 0, right? What if we used a different method for calculating this? What if instead of vanilla matrix inversion, we used super complicated, iterative, massive, multi-frontal methods for jiggering heuristic AI something? Would we be able to find a solution then? No, it doesn't matter. It doesn't matter at all, right? Like whatever method you're using to find this, the fact that you cannot, the fact that the determinant is 0 and that you would get 1/0 in your inverse calculation invalidates anything else, which is a little bit of a problem, and which is something that you guys are going to have to deal with because this is the other edge of the sword. A lot of calculation methods, if you're using something called least square regression, least square solution or pseudo inverses, you're still going to get an answer. It's going to give you an answer, but that answer doesn't mean what you think it means. So blind application of these tools, pseudo inverse, least square solution, anything like that, you're going to get something, but it's not going to be the right something. Okay, and where I'm going to do my best to kind of steer you towards the right ones, but you have to understand, like, if those lines cross, like never cross or cross infinite times on your graph, you will not, whatever solution you're getting is not the solution you think you're getting. Okay, if dude meant to say 500 instead of 400, anybody know what that does? I got a lot of answers from you guys. How about over here? Don't make me poke questions. Yeah. You're still going to have no solutions. What's your graph going to look like? You got it. Right? All of that constant vector is doing, the elements of the constant vector, is adjusting the spacing between those. But there's still no real solution. There's still no unique solution. Right? You might be able to get all the solutions. Otherwise, you're just going to have that gap and you're not going to be able to get it again. In this case, what is your determinant? Got it. Right? Which is also bad. Right? So in one case, we were doing the inverse. When we did the inverse, we had 1 over 0, which is infinite, which is useless. In this case, we have infinite, in which case 1 over infinity is quote unquote 0 by convention, if not mathematical rigor. Okay. If we do elimination, what we're going to get is 0 is equal to 100, which of course is nonsense. Okay. Note that the equation for A, the matrix here, hasn't actually changed. Oops. Right? When we played around with the element of this constant vector from 400 to 500, the matrix itself didn't change. Does that mean anything? Does that suggest anything to you guys? Do you know what I mean, first of all? Yeah. I'll go back because I think I skipped a step there. Okay. When this was 400, we had the matrix equation 20, 20, 1, 1, x, y. Can you guys see? Should I turn on the lights? Better? Yeah. Equal to 420, right? The A matrix is this guy. Sometimes I like to do that with a bar across, just like as an equivalent to the little arrow over the vector. Okay. That's case number 1. And this guy doesn't have a solution. It doesn't have a unique solution, right? When in the second case, it was, that's useless. 20, 20, 1, 1, x, y, 520, right? And in this case, we didn't have any solution at all. We had parallel lines, right? Neither of these two cases give you a solution, a unique solution, right? But the A matrix in both cases is exactly the same. All that's changed between the two is your constant matrix. So what does that tell you about the solvability of this system? Does it depend on your unknowns? No, right? Nor can it, right? I could just on a whim say instead of x and y, this is z and z2, right? The numbers don't mean anything. It's all a variable. It's all abstracted. Does it depend on your constant vector? I hear one yes. Anybody want to contest that? Okay, anybody who says no, put up your hand. Okay, everybody who says, what was the original question again? I've forgotten now. I've mixed myself up. Okay, let me try that again. Anybody who thinks that I haven't had coffee in like 2 days now. All right, anybody who thinks, raise your hand if you think that the constant vector has anything to do with the solvability, being the ability for you to find a unique solution of this equation. So raise your hand if you think it does. Okay, hands down. So everybody who didn't raise their hand, right, you think the opposite, raise your hand. You guys are actually right, as it happens. The constant matrix out here determines which solution you're going to get, what intersection you're going to get. But whether or not the system is solvable at all only depends on the constants. Right? Which is funny, which doesn't like is kind of weird, right? But consider we stopped getting a solution. So in the first case, when we had 2050, 1, 1, we could solve that, right? And if you wanted to use a different numbers here, right, you could say 615, and you would still be able to solve that, right? You could say 300 million and 100,000, and you would still be able to solve that, right? We only had problems because we did two things at once, right? We only had problems, and then I'll get to you, when the price of tables dropped. And then depending on our constants, depending on our budget, we either had infinite solutions or no solutions, both of which aren't really helpful for us. You had a question? Bingo. Bingo. Absolutely, right? And when the slope of each line is the same, you got it, right? And that turns out to be all that matters. And more than that, there's more, and we're going to talk about that when we get to preconditioners, which is next week, which isn't part of normal numerical methods, by the way. They don't normally get to preconditioners, and I don't know why. But anyway, we're going to get to it. I'll show you guys. I'm spoiling things. I'm too excited. I'm ready to go. All right. By the way, if you're still kind of struggling with that, you can also think about what it takes to calculate the inverse of A. Because once you have, right, like if you were to do this, not that you ever should, but if you were to do AX, somebody remind me to bring my markers next time. Right? If you were to do that, X is equal to A inverse B. The complicated part is calculating A inverse, right? And A inverse doesn't care about B. You can get A inverse first and then apply it to as many B's as you want. But the solvability requires your ability to calculate A inverse in the first place. And that's what breaks down. Okay. So 2 lines, 2 unknowns, right? Solution can either be a unique solution in exactly one place, or it can be the parallel case, in which case you have everywhere or nowhere. In this case, and the problem with this is that these two equations are linearly dependent. If I just take this and I multiply 20, 20, 20, I get exactly this guy, right? Similarly, even if I did have 500 out here, it doesn't matter because I would have knocked out my unknowns. And then I would have 0 is equal to 100, right? This is what linear independence and linear dependent means, right? This is the way that I now think about it, not the way that I thought about it at back in my day, right? But it is literally one equation depending on some multiplication plus a factor of the other one, right? So this guy, if you multiply just this guy through by 20, you would get exactly this one, right? If your budget increased and you had 500, then you would have to multiply through by 20 and add 100. And then you would get exactly this guy. Anything where you multiply and then add a constant is a line. It is a different notion of linearity. It's a generalization of linearity. But that's what linear independence means. I saw a question? Oh, good. All right. Right. Okay, and we talked about this. In the case where the determinant of A is 0, the matrix is called singular. Singular matrices are giant pain. But it's surprisingly common. Yeah. Okay. So, let's review. In case number 1, when we calculated that determinant, right, we had 20, 50, 1, 1. we calculated the determinant to be minus 30, right? In case number 2, we found the determinant to be 0 because the lines were parallel. Okay, so somebody tell me the significance of negative 30. Why is negative 30 work and 0 doesn't? Why is negative 30 magical? You already answered. And answer again. Yeah, you answered too. Somebody who hasn't answered. I'm going for the back row there. Gonna be one of you guys. Okay, third person in. What's the magic of minus 30? Why is minus 30 a magic number? Hey, negative bonus marks. You coming in for the save? Yes, yeah. So that's how you get the number, but 0 breaks it. When you calculate that and you get 0 for the determinant, it doesn't work. So why does it only work with, right? I'm giving you guys a hint there. Why is it only working with negative 30? What's the magic of negative 30? I'm back to the original person, and you're not off the hook. The fail safe. They failed. What's negative 30? What is the significance? Well, it does exist in a number, right? Somebody tell me. Okay, opening it up to the floor here. Shout it out. What's the magic? 0? You can't do 1. Right, so what's the magic of negative 30? If I had negative 45? That's okay. Negative 30 means nothing. It doesn't mean anything whatsoever. 0 matters. Infinity matters. What about negative 3? Would that work? Okay, what about negative 0.3? What about 0.0000000003? Ooh, good thinking, right? So if you didn't have to worry about rounding, 0.00000003 would still be absolutely fine, right? That's okay. So what's the magic? Where does it change over from bad to good? Is it a sharp line? Right? Whenever you get, like, nature doesn't normally work this way, right? That you have, like, everything is fine as long as you're non-zero, and then 0 and bang, you fail. It blows up in your face, right? Like, it's kind of janky, right? We had a spoiler that your numerical error comes in, right? And your round off error. So it'll work as long as 0.000003, as long as you got infinite precision, that's going to work. We don't have infinite precision, right? Refer to last week's lecture. So let's do this a bit more formally. So we saw that the determinant goes to 0 when you adjust the price of tables. Let's play with that. So we're going to set the price of tables to 20 minus epsilon, right? Epsilon, just a constant we're going to play with. Epsilon typically is something small. Whenever you're talking about like numerical methods or in computational whatever, like epsilon, some people will call that machine precision. It's just like kind of a very small number. Sometimes people would say it's the round off, right? It's the point where round off comes in. Okay. If you say that tables are equal to, instead of 50, they're 20 minus epsilon, right? You grind through your math. What you're going to find is that your determinant is actually equal to epsilon, right? In which case, if you don't believe me, just go through the math and you'll see it come out. I don't have time to do it here. So as epsilon goes to 0, i.e. as you get to 20, which is the point where those two lines depend on each other, right? They're parallel, they depend on each other. You can no longer like solve this problem, right? And this is not so clear in my mind. So actually at this point, one sec, I will point you over to here. So if you go over to this tool, again, that's down under the importable modules, and you have to click next over to get to it. But it's pretty nifty. Thank you, Joel, for doing this, right? You calculate 30, and lo and behold, these lines become more parallel, right? You can calculate 25, you get more parallel still. 21, right? Oops. That's why I don't like live demos. Okay. Technically, So check this out. When the tables are 21, I can still find a solution, right? It's up here. Joel was nice enough to program this in so we can see it. When it was 50, no problem, we found 10 and 10. Okay? If I do 21, I can still find a solution. If I do 20.1, I can still find a solution. No problem. But the lines are almost overlapping. And what round off error and numerical error does is it adds thickness to these lines for like the graphical equivalent of this, right? So where are these two lines actually overlapping? Is it here? Apparently, analytically, it is here. Could it be over here? Well, you know, they're overlapping too. Within the noise, within the round off error, yes. You could be forgiven by thinking it's over here. Turns out the computer also gets confused. Okay? This is called the conditioning of your system. Okay? Here's just a table of me playing around with epsilon values. You see as epsilon gets smaller and smaller and smaller, the solution still exists, but two things happen. First of all, it moves far away, but the rate at which it's moving also increases. You're into a limit behavior, into an asymptote to get there. Okay. This should raise alarm bells, the idea that like it works almost, and then you hit 0 and all of a sudden it doesn't work. Round off error is about 1e minus 16, 1e minus 20, somewhere around there, usually 1e minus 16. So we're in the range, right? Which means, say you had an equation, say my price of tables actually was $20.000001, right? And that was the actual thing. It was no longer an exercise. Could I still find a solution? Yes. Problem is that even the elements of that matrix are now within the throwing distance of round off error. And as soon as that happens, you've got a recipe for failure, to be entirely honest. Right? Because even just the act of taking that number, putting it into the computer, you're already into like the round off region. Okay. We could, from the original equation here, we could just take this equation and multiply it by 3. Right? If we did that, would that change our answer? Sorry, this is 700, so we're actually solvable again. You want to know like what really just drives me insane and what I'm going to snap at one day is going to be like dry useless markers or dry pens, stuff like that. Yeah. Right? Could we just multiply the first one by 3? Yeah. Shoot. It's you can just consider it to be a small number. Yeah, it's just a variable that yeah. It's kind of the go-to for a small number. Yeah. No. Right. So back to our original equations. This worked, right? We found 10, 10. So what if instead of doing that, this was 60, right? So we're just multiplying by 3 everywhere. 21. Would that change anything? No? Anybody, like super quick, you can see it works out, right? What if we multiply this guy by negative pi? Does it still work? Right? So that the magnitude of these guys doesn't matter, right? This affects the determinant, the calculation of the determinant. But as we said, that size of that determinant doesn't matter. Neither does the sign, actually. Yeah. Unit is the standard, right? Which is also why the determinant is technically the area, right? If you wanted to calculate that area, I forget what all these terms are. You would do the unit vectors of those lines and then calculate the determinant based on that. Turns out the determinant calculation is also really easy if you do those normals, if you do those unit vectors, but doesn't matter. Yeah. Right? So we can just take these equations and just multiply them through by any number we can imagine, including epsilon technically if we wanted to, but we won't go there. Right? All that's important is The magnitude of those equation, sorry, what am I going here? Complete brain fart. All right, all that matters is the normalized direction. In other words, the unit. What you're talking about is the unit vector, right? Like if you put this into a line and you do your calculations, you reduce it, you can get the total, right? The total magnitude of that vector has to be equal to 1. No problem. Okay. What we need to do is figure out some measure of the magnitude of the matrix A. Same way that we would take that vector that was some magnitude and we would reduce that down to 1. We want to do the same thing with a matrix. There are a few different ways to do that. These are called the norms of the matrix. A vector, if you have a vector that looks like that, your norm is the magnitude, right? Matrices, not so simple. Turns out there are a bunch of different ways to find the norms of this. Okay. The Euclidean norm is the easiest one. Oh, sorry. Yeah, the Euclidean norm is the easiest one. And what you're going to do there is you're going to take, am I jumping ahead of myself here? Yeah, a little bit. Okay. I should reorder this. Doesn't matter. Okay. What you want to do is you want to find out some measure of the magnitude of your matrix. And the magnitude of the matrix corresponds to the determinant, right? And as long as that magnitude is non-zero, then your matrix will not be singular, and you can proceed with your inversion. Okay? One of the easiest ways to do that is using matrix norms. There are a few. One way to do that is kind of an extension of the way that we do Pythagorean theorem, right? We take the square root of each element squared, the sum of each element squared, right? Square root of a squared plus b squared is equal to c squared. You take the square root of that, now you've got c, okay? And that's your magnitude. In general, what you can do is do the same sort of thing for a matrix, in which case you've got the Euclidean norm, but it doesn't mean the same thing as like the length of a vector. You can generalize it, and a lot of people will talk about this. It's called the P norm of your matrix, and it's kind of an extension of that. So what you're going to do is you're going to take each element of your matrix, you're going to raise it to some power, right? And then you're going to sum that and take the same powerth root. This is the equation for that. For 2, it's just the Euclidean norm. If P is infinite, this is one of those cases where infinity is actually fine. You actually just find the max element of it. The importance of all this is this will give you an example of the size of your matrix. And as long as the size is non-zero, your determinant will be non-zero. It's the size of the transformation, actually. As long as that determinant is non-zero, then you can stand a chance of doing that. The condition number for your matrix, I'm jumping around a little bit, I apologize. Okay. The condition number is the measure of how you transform one way and the other way. Okay. Formally, it's defined as the determinant of the forward transformation A divided by the determinant of the inverse transformation when you go back the other way. That requires you to solve for what the inverse matrix transform is, which is complicated. What you can do instead is calculate the norm of one of your matrix, and as long as that's non-zero, then your condition number is pretty good, and that's kind of a shortcut way to do it. The goal for this is you want to make your matrix well-conditioned. Well-conditioned means that you have an area of your include, well, what do you call that, polygon, right? That is, you want it to be non-zero, but you also want it to kind of be normalized. The ideal condition number is when your matrix is 1. And what that means is that you're going to be able to transform forward, you're going to be able to transform backwards. I think I'm seeing a lot of shaking heads here. How to explain this? Sorry, one second. What's that? No. When you apply a transform to a vector, right? That's what a matrix is doing. You're taking that vector and you're changing it somehow. Depending on the size of your matrix norm, right? You're going to be expanding it in certain directions, or you're going to be scaling that vector. If you scale it too much, you scale it small, the inverse is going the other way. The ideal case is when that scaling doesn't really change the magnitude very much. Because then you can move forward, you can apply that transform, it moves a little bit. You can move backwards and it hasn't really changed too much. If that vector gets scaled off to infinity, you've got a bit of a problem because you can't invert that. You can't go back the other way, right? What the condition number of the matrix is doing is it's testing how much that scaling is changing going one way and the other way. And if it is large, then what that means is that one scale is driving it off super big, in which case the reverse, the inverse is going to be problems. If it's super small, if you start off with a vector and you shrink it down to almost zero, and then you go back the other way, then it also breaks down. It's just kind of the inverse. So the ideal transform, the ideal behavior of the matrix is when your condition number is 1. In that case, you get a vector that kind of goes like that, and your transform is going to move it a little bit. Yeah. When the transform itself is infinite, because it also means that when you start off with a vector, you transform it and it goes to infinity, an infinite magnitude, right? If you try and do that backwards, it's also going to fail, right? It's the same as going like 1 over 0 and 1 over infinity. It's just considered the same. The nice thing about the condition number is that you can calculate it without having to know the inverse. So there's a nifty NumPy tool that is just finding the just like cond of the matrix, and it'll just tell you that number. You want that number to be close as 1 to possible, close as possible to 1, because that means that you can do these transformations. And as we'll see coming up probably next class, that also means that these calculations are robust. They're not subject to numerical error. When this guy was, oops, change that. Oh, actually, it's here. Okay, so this guy, you calculated it here, right? The condition number turns out to be this, 9.67, right? So if you take the determinant of A and you divide it by the determinant of the inverse, A inverse, this is the condition number you're going to get. You don't have to do it that way. That's the analytic answer. Numerically, you can also calculate it based on the norms of the matrix. That's how cond is working underneath. That's why I wanted to tell you guys about that, but I think that got a bit too far off track. As you go here, right, watch what happens to this condition number here. Right? Now we're at 4,400. Now we're at 840. Right? Now we're at 8,000. And it gets worse and worse. Right? So this is a way that you can just apply a single operation to the matrix itself and find some indicator of the solvability of it. If you go to 0, of course, that's infinity. And if you did change this to anything else, of course, that doesn't matter about the condition number. Does that make sense? You guys, you're not going to have to, I won't ask you how to calculate the condition number, right? But we're going to be using condition number to judge whether or not the matrix and the system of equations is a good system that we actually want to solve. It's going to come important when we talk about the preconditioners, because the point of a preconditioner is to take a system of equations that doesn't want to solve and turn it into a system of equations that solves a whole lot easier. But we'll get to that. That's next week. Any questions? Got one question? Yeah. Oh, yeah. Aha. Right. So how would we get it to 1? If we did, I don't know, actually, that's a good question. I think what we would want to do is we would want to have the square of the coefficients equal to 1 on both sides. But I'm going to play around with that and try and figure out how to do it. Yeah. A condition number that is not 1. Anywhere away from 1 is bad. Yeah. If you get too high, then it's bad. If you get too low, low is the inverse of high, and it's still bad. Yes. Yeah, exactly. Yeah, I wanted to get into well, you know a lot about eigenvalues? All right, hold on. So condition number is technically related to eigenvalues. I'll see if I can get a coherent explanation by Thursday. Then come back to it. Yes, yeah, exactly. The eigenvalues are the way that you're transforming that vector in terms of the scale in one dimension and the other dimension. And it turns out that if you have a very large extension in one dimension, but a very little dimension in another, if a little scaling in another dimension, then your transformation is hard to do. Right? Exactly. Right? But moreover, that difference in magnitude between the small and the large gets into round off. There's a tie in there. Yeah. But in order to get that, we need to jump ahead to eigenvalues. And it's one of those things that is the cure worse than the disease. So I'll try by Thursday. I'll see if I can come up with a better explanation. Yeah. Yes. How numerically? Closer to 1.
The more solvable.
I'll do my best to come up with a better explanation.
I understood all the way up until the purpose of the condition number.
Yeah, no, I know. No.
How solvable it is, and for now, just know that 1 is good.
Numerically, how solvable.
How numerically solvable it is, and 1 is just good for now.
1 is the ideal, because then it's easy to go backwards and forwards. Yeah. Okay then. I'll do my best to come up with a better one for Thursday.
Thank you.
By all means, take a look at Wikipedia. Eigenvalue singular decomposition.
Overloaded.
Oh, how do you get that? Numerical methods. Okay. Okay, guys, let's get started. I have no idea who this is. Sheets that are apparently all over the class. Be careful about signing up for things that are probably going to ask for tens of thousands of dollars from you directly for the joy of buying a flight ticket through them. But anyway, not that I'm bitter. Okay, I want to revisit conditioning because I don't think that was a great job communicating what the idea behind it is at the end of last class. It was kind of rushed. So I wanted to circle back and actually, on the way in today, I was chatting with them. So I have an Android phone, and I changed my Google Assistant to Gemini. So I was chatting with it about how best to communicate what condition number is for matrices, and it gave me a really great idea. So I really like it. So I'm going to present it now. But by the way, if you have an Android, change your assistant to Gemini, and then you can just start talking to it. Fantastic for long car rides and stuff like that. Really, really like it. Okay. About halfway through last class, we started talking about approaching the singularity. So you have this well-formed equation where you have, let's see, I have to be mindful of time because we have to finish direct solvers by the end of tomorrow. Okay, so we had a well-formed equation. I think it was something like 20c plus 50t is equal to 700, right? And then we had c plus t is equal to 20. Right. And what we found was that as 50 went to 20, right, this had a solution, no problem. 40 had a solution, 30 had a solution, 21 had a solution. But as you approach 20, all of a sudden you no longer have a solution, right? And your system becomes non-invertible. Okay. And what we talked about was that this is related to the determinant of this matrix, right? 20, 50, 1, 1. And as that determinant becomes 0, as long as it's non-zero, you can solve it. The matrix is singular. But as soon as you get to 0, then your matrix is singular and you can no longer do this. Okay. So what I want to do here is let's set the cost of like the tables here to 20 plus epsilon just being a constant. We're going to take it to 0, right? Put that in, calculate the determinant, and what you find is that your determinant is actually just equal to epsilon. So super convenient. Obviously, this is a problem when epsilon goes to 0, i.e. when the error here goes to 0 and this approaches 20, your determinant becomes 0 and then you have a big problem, right? Because you can't invert it anymore. Okay. When you solve it, you can solve it and you get to something like this. The number of tables is 300 divided by epsilon, right? And that again is a problem because as epsilon goes to 0, this becomes infinite. While it's approaching 0, however, you can find still T's and C's, right? So as you're getting closer and closer and closer to 20, first of all, the number of tables and chairs starts to get huge, right? You get these massive by magnitude, negative being small, by magnitude starts to get very large, but also the rate at which it's approaching these large numbers, positive, negative, infinity, gets increasing, right? What this is, what we're talking about, so this one is a problem, right? 1e minus 20 is a problem because 1e minus 20 is very much in the realm of round-off error, right? Round-off error and numerical error essentially inherently introduces this uncertainty into your system. Just by virtue of representing this function in a computer itself, you have some uncertainty. That uncertainty is less than 120, and therefore your uncertainty on the other side, on the output of this function, becomes very, very large. Big problem. Enter the notion of conditioning. Okay, this section is new. I rewrote it last night. That was fun. Right, okay. So round-off error, truncation error introduces an inherent uncertainty in all your numbers. The conditioning of a general function, this isn't even linear functions at this point, relates how the uncertainty in the function output b, right? So usually you would write f of x, usually you would write it like this. F of x is equal to y, right? Later on, spoiler alert, we're going to revert this back to linear systems, in which case we get ax is equal to b. So I'm just starting off this by saying this is b. Okay, that's why there's b on the other side. It's y, it's b, it doesn't really matter. It's the output of the function. Okay, so you have a general function, vector function. F of x is equal to b, right? And the conditioning relates how the uncertainty, this is a little bit funny way to describe it. It relates the uncertainty in the output to the uncertainty in the input, in the worst case. And you have to say in the worst case there, and you'll see why in a second. It is a function of it is a property of the function f itself for in most cases. In nonlinear cases, because your function behavior can depend where you are in the function range, i.e. where you are in x, right? You can call this a local property of the function. Linear functions have the same behavior everywhere. Therefore, this is a property of the matrix itself. It's related to the distortion of the input uncertainty to the output uncertainty. And that's a really weird way to think about it. Right? Commonly, what you're kind of tempted to think is, okay, you have a little bit of uncertainty in your input, and that gets magnified. And now a little bit of uncertainty in the input becomes a large amount of uncertainty in the output. This is kind of like the intuitive way to think about it, right? This is definitely the way that I started thinking about this, right? That's wrong. Okay? Don't think about it that way, because that implies the reverse. If a little bit of uncertainty in x results in a large uncertainty in b, then the converse should be true. If you started and you solved your system, so you took a little bit of uncertainty in your output and solved for the input, if it was a matter of amplification, then that should shrink. And you should be able to do the inverse of the function more accurately than you were able to do the forward. Does that make sense? Yeah, it's just kind of like you're zooming into it, right? But the conditioning number is not about that. That's not the key of it, right? And that relates back to this whole in the worst case thing. I come back to how we define it, and then I'll give you the example, right? Well-conditioned functions have output uncertainty, which is roughly the same as the input uncertainty. And what that means is that you can move between those two easily without this distortion effect, right? Ill-conditioned functions are the problematic ones. Not surprisingly, they have ones that distort this sphere of uncertainty. I'll show you the example here. Okay, but first, math. Good, 8:40 in the morning, and here's some fun math. I was trying to play around with getting JupyterBook to correctly format these equations. So if there is some equation like funny business and things aren't aligned at the equal sign and like this just duplicated right here, forgive me. I'll come back to that one. Okay, let's get into some algebra. Let's say that our input x, right, has some uncertainty delta x. Just raise your hand if I lose you guys at this point, okay? Just interrupt me. So you have x, that's your input. You have this uncertainty delta x. Is the delta x positive, negative, right? Doesn't really matter at this point because we're going to be taking the maximum impact of this. Similarly, you have your output b, and we're transforming that to have a little bit of uncertainty in b. Good. When we do the matrix equation, right, we're going to do, for the linear system, did I just skip over that part entirely? Okay, whatever. Linear systems, f of x becomes a of x, right? You're in linear systems, good. Okay, for linear systems, you now have a times your new x, which is x plus delta x, is equal to your new b plus the uncertainty in b, right? Because you have a linear system, yes. Sorry, turn off or on? Off. There. All right. 8:40 in the morning. Lots of algebra. Lights off. This can only go. If I hear any snoring, negative bonus marks. Okay. Negative bonus marks is a mine. It was like my high school teacher or something who came out with that one. I love it. Okay. Properties of linear systems, of course, is distributive, right? Which means you can take a times this sum, distribute it over. No problem. But now we know that ax is still equal to b, right? We started off with that. So if there's no error, then we just have this, which means we can subtract it off from here. And all we get is, not surprisingly, right? The matrix times the uncertainty in the input is the uncertainty in the output. Similarly, we can just invert that. No problem at all. Okay. Now we're going to calculate the relative error in the input. And we're going to consider the norm of that vector, okay? So the norm is this concept that says if you have this vector, right? The most familiar norm is the magnitude of the vector. It's not the only norm. It turns out, and I went over this, and I didn't get into this quite quickly enough. The Pythagorean norm, the Euclidean norm, is the most familiar to probably you guys at this point. There are other types of norms, including the L infinity norm. So I'll show you what the equation for norm is. The L2 norm is the Euclidean norm. Literally, you're taking the square root of each element squared, right? The infinite norm is the infinite root of each element raised to the power of infinity, which boils down to the maximum of your vector, right? That's a little bit of context, but you won't need to know that until you're actually programming this stuff and you come across it. Okay. Let's calculate the relative error in the input, considering the norm of the resulting vector. Okay. So we're going to take, can you guys see this or is this too small? I'm just going to zoom in. Relative error, we talked about already. It is just the uncertainty, the magnitude of the uncertainty, right? Divided by the actual value. So you've got magnitude of delta x over x. But we have an expression for this. So we're going to use the expression of this and plug it in like this. A inverse delta b over x. Bear with me. Similarly, we're going to do the same thing for the output, right? Mag. And now we're going to use the original equation, ax is equal to b, and plop that in here. So now we've got the relative errors in both your inputs and your outputs. And we're going to divide those. Okay? When you do that, you chunk through the math, right? This becomes the inverse of this. You shuffle around your terms. And now you get to this expression. This guy is only a function of delta B, right? Your uncertainty in B, your outputs. This guy is only a function of the original vectors, your input variables. Okay? Everybody with me so far? This is just like straightforward algebra. Good? Good. We now introduce the norm of a matrix, and we're going to use it to separate this matrix vector product. So matrix vector results in a vector. Everybody knows how to take the magnitude of the vector. Fine, right? What we're going to do, trust me, guy, we're going to come back to it later. This is one of those things that like you have to know what's over here before you can understand the derivation over here, but you can't get over there until you've done this part too. Like it's why like math, like learning math is a really nonlinear thing. But anyway, okay. Trust me, guy, there is such a thing as the norm of a matrix. The same way that you would take the magnitude of a vector, you can take the magnitude of a matrix. We'll circle back to that one. But it has an interesting property that the magnitude, the norm of this vector, right? Matrix times vector is a vector, is always less than or equal to the magnitude of the matrix times the magnitude of the vector, right? And it's one of these triangle inequalities that's generalized to multidimensional so-and-so, okay? Why this is nice is because we're going to be concerned about the maximum. And the max happens when this is equal. So we're just going to plop it in. We're going to define our condition number as being the maximum of this, right? The max over these delta B's. So we've got that. The maximum between these for different combinations of delta B and X is the product of the maxima. If you don't believe me, just think about that for a little while, right? And now, because of this nifty property, we can actually cancel out this norm of the vector. We split this up, right? This becomes the norm of A inverse, norm of B. That norm of B cancels out with that norm of B. And all we're left with is the norm of the matrix inverse times the norm of the matrix itself. It's kind of funny to look at it that way, but it has some interesting properties. And finally, we can talk about what we actually mean here. First of all, if you were to do the inverse of the function, right? If instead of ax is equal to b, you defined a new function, which is x is equal to cap c times b. So you're just inverting that product, that function, right? Is your condition number of the inverse going to be the same as the condition number of the forward? The answer is yes, right? And you can just see that if you replace a by a inverse, right, this product just swaps and the order of multiplication doesn't matter. So no problem. This is funny and this is counterintuitive. And the first time you see this, you're going to think that I like had the wrong breakfast cereal. Okay. So what this means in the application of the condition number is that the uncertainty, the relative error in the output is at most, right, less than or equal to, it's at most this condition number times the uncertainty in the input. But at the same time, right, which sounds like a magnification thing, but at the same time, the uncertainty in the input is at most the relative error in the input is at most the relative error in the output. Which is weird, right? Like you wouldn't do this with an equal sign. Right? You can't do this with an equal. If you actually replace this equal sign here, then obviously like it wouldn't work. You guys see that? Yeah. If you don't see that now, you will when you're studying for the test. Right? This works because we're not in equality, we're in this less than or equal to. Where should I go here? I'm going to go here. Okay. Live demo. I hate live demos, but I think it's worthwhile. And then I got to pick up the pace here. So what this means is if you start off with one coordinate system, right? Matrix transformations are all about transformations of coordinates, right? Everybody remember that? Okay, good. When did you guys learn that, by the way? Is that first year or is that second year? First year? Okay, good. So we are moving this course to second year. So I need to make sure that, so is like linear algebra, is that all first year? Yeah? Okay, good. Do you guys talk about eigenfunctions, eigenvalues? Yeah, in first year? Yes. All right, good. Good. So you have a coordinate system. You have some vector, x, right? And through this matrix function, you're going to get to, can you guys see this over there? Yeah, okay. You're going to get to some new function or some new vector b. Make sense? Okay. Let's take, there are a few different ways to do this, and I'm going to have whatever student I get to help like develop the interactive elements, I'm totally going to get to do this, okay? Let's take a small little circle around our vector. And this is delta x, right? So you've got your actual vector plus your uncertainty, which defines this circle. If you calculate the impact over there, what you're going to get is something that looks like that. This is, well, what would that be? Okay. So you're going to take this little delta x, you're going to hold that magnitude, and you're going to sweep it all around. So you get a circle. You repeat that transformation, and you go around, and you get this kind of distorted figure here, right? If, does this make sense so far? Okay. Here's the leap. Now, let's take another one. Let's take another circle over in your B domain here. Hold on. Can't see that. So this is delta B primed. Okay. And we transform it back to here. Anybody know what it's going to look like over here, roughly? This is going to get the opposite of this transformation. So delta B is going to look something like that. I should not imply things that I don't mean to imply here. Too many things. Delta X primed. Does this make sense? Right? Whatever transformation you're doing to that thing, you had to, because that transformation is reversible, it has to be reversible because it's linear, right? That extension, right? You could be excused to think that this magnification just results in an extension. And that if you only had the error in that extension, then it would be like a contraction and you would get a more accurate answer over here. But because we're in the worst case scenario, you're actually looking for the entire potential of the random element, right? So this one, the worst case scenario is here. The worst case scenario here is this guy. And if because you don't build, because uncertainty is inherently random, right? The impact of Randolph error and truncation error is going to be random, insofar as computers can be random, right? I never actually talked about that in this course. Computers can never be random. I spoiled it. Okay. Because of that, unless the quantum guys kick in here, but I don't see any of them, so even better. Right? Because of that, it becomes this distortion field instead of this extension field. You had a question? Ooh, because you look at your condition number. You calculate your condition number. And when you calculate your condition number, then it will tell you. So what happens, K is 1, sorry, kappa. Kappa being 1 means that the difference between this guy and this guy is the same, is 1. This wouldn't actually happen, by the way that I drew this, but what kappa means, I have, yeah. So kappa being 1 means basically that the transformation is a certain type of transformation. It means a very simple transformation. Yeah. I'd have to think about that one, but the magic here, and it comes back to this again, it is the relative error, right? So it's all this is saying is about the uncertainty over the magnitude of the vector, versus on the other side, the uncertainty of that one over the magnitude of that one, right? So it has to be a large vector to have kind of a large uncertainty, or it gets compressed. But your particular question, I'm not sure off the top of my head. We'd have to think about that one. Let me move on, because I got to catch up. Okay. Does this look familiar to anybody? Or whatnot? Okay. I see some head nodding, right? Here I transferred this away from the origin, right? My x and my b are both away from the origin. Let's redo this. Ba, ba. I've got my circle here. Ba, ba. Oh, I don't even need to do that. Do it like this. Okay. Where this is a x. So that transformation. Anybody know what this vector here is called? Anybody want to have a guess? The maximum transformation, the maximum squashing, right? Extension, skewing of this guy. Nope. Oh, that would be way too easy. See, so, okay, yeah. So if that were the condition number, then the inverse transformation, this guy would be a contraction in the error. It's not. Anybody else? This is, what's that? Eigen, right? There you go, yeah. Right, I just asked you guys about it like 5 minutes ago. Of course it is, right? The point at which on the original one, your transformed image is just a multiple of that original vector. Like this guy over here becomes, what was it? This guy becomes over here. This guy over here gets stretched out to here. This guy becomes over here. There's only certain vectors that the transformation only results in a scaling, right? This guy, for this particular point, equals lambda x, right? Is there another point that has the same property? This is an eigenvector. This scaling is an eigenvalue. Is there another special point here? The answer is yes, right? And it's here. This guy is another eigenvalue, another eigenvector, but it is the smallest. It turns out that the condition number is the ratio of the largest eigenvalue to the smallest. The maximum that an uncertainty in this guy is going to have is the largest eigenvalue by definition. You can see it right here in this picture, right? The largest impact that an uncertainty here is going to have is the largest eigenvalue, right? The largest uncertainty in the inverse turns out to be 1 over all those eigenvalues. It is the original smallest eigenvalue. And the nice thing about this is, first of all, eigenvalues can be calculated iteratively and efficiently. We'll talk about that 12 weeks from now, right? I told you we were jumping way ahead on this one. But also, if you look at this, this form isn't very useful because I'm calculating the condition number with the inverse of my linear system, right? That's not really useful because that's saying solve your problem and then tell me whether or not you can solve it, right? So it's kind of like this analytic thing, but because you have this eigenvalue property, if you can find your eigenvalues of your original matrix, your largest and smallest, you don't even need all of them. All you need is the largest and smallest. You have 10,000 by 10,000 matrix, you have 10,000 eigenvalues. In general, all you need is the largest and smallest. You can calculate your condition number. Yeah. Yeah. It's the semi-major axis. Is the technical term, I know. It is so this transformation takes like a circle into an ellipse, right? The way that you would write an ellipse and the way that you would characterize an ellipse is your maximum size there and your minimum size there, right? And if you look into like just drawing an ellipse, you're going to find semi-major axis and semi-minor. Major is the largest, minor is the smallest. And those are actually your eigenvalues, which is kind of nice, but they are also the bounds of this uncertainty distortion. Okay. Now we're 25 minutes behind. Very quickly, matrix norms. Oh yeah, so sorry. The ideal case where you can move, most cases we're interested in the backward problem, right? We have AX is equal to B, all fine and good, but what we actually want is X is the X that solves that equation. X is equal to A inverse times B, right? When the condition number is as small as possible, which turns out to be 1, condition number can never be smaller than 1, and you can kind of see that actually from the equation. When it's 1, it means that this distortion doesn't really happen. The circle in X corresponds to the circle in B, and you can move kind of between these two relatively easily. When it is not equal to 1, you have this distortion effect, and now your round-off error is going to come in and kick you in the teeth. Okay? But remember, this is a property of the function itself. It doesn't actually matter because the uncertainty has this random element. It doesn't actually matter where your vector is for linear functions. For nonlinear functions, different case. Guess what? We never actually solve nonlinear functions. We actually just make them into linear functions. Spoiler alert. Yeah, when it's 1, it means that a little bit in the output gives me a little bit in the input, and they're roughly the same order of magnitude. When that's not the case, then you're in trouble. Then round off is going to come in and hit you. Okay, super quick. So condition number being 1 is the good one. We're number 1. We want condition number being 1. Anything that is not number 1, when we talk about preconditioners, we're going to make it number 1, and then we're going to solve that. Okay, that's how that works. Very quickly, matrix norms. Everybody's familiar with Euclid, Pythagoras, right? Square root of the sum of the elements squared. In fact, there is this generalization. If and when you come to it, and we might talk about it with error for a differential equation, the partial differential equations, right? You can also do the L infinity norm, which is the max. When you talk about matrices, there isn't a single definition of a matrix norm. There are a whole bunch of different ones, the simplest of which is called the Euclidean or Frobenius or L2 norm of a matrix, and all that is the square root of the sum of all of the matrix elements squared, right? Makes sense. That gives you some sense of the magnitude of the matrix. Problem is that that's not unique. There's also the infinite norm, and there's actually all kinds of different norms. The reasons why you would want to use all those infinite norms is like advanced numerical methods. Okay, just putting that in for completion. All right, computational complexity. Did we talk about this? I think we did talk about it yesterday, but it was after the condition number thing, so I don't know how much this sort of stuff sunk in. Okay, we are concerned. So we've been talking so far about like this error propagation and like the downfall of finite precision and things like that, right? What we're going to talk about now is the amount of oomph that it takes to actually do some of this stuff, right? And the way we're going to characterize that is through the computational complexity. Computational complexity is roughly, everything is going to be very like kind of hand wavy in a highly mathematical specific sense, right? We're going to use this big O notation again. So the idea is you have some algorithm and it depends on the size of your inputs, not what type of input you have, but the size of it. So a linear system with a single input is just like A times, well, AX is equal to B where it's just all scalars, right? AX is equal to B is super easy. We're generalizing that. Now we have matrix. This is a vector of size n, right? And this is B as a matrix of size n. This is n by n, okay? What we're concerned about is the size of this input vector, n, right? The size of the input vector almost always, actually, no. The size of the input vector typically means that you have like an increasing size in the matrix, right? Because how else are you going to get n times n, like a matrix n by n times a vector n, right? Does that make sense so far? Is that like linear algebra? Yeah. Pardon me? What size is the input vector? I still don't hear. I'm sorry. No, not the norm. The number of elements in your vector, right? The dimensionality, exactly. Pardon me? No. Yeah. Yeah. This is the tricky part, right? It's nothing to do with the value of that vector. It's your dimensionality of your problem. That's a great way to say it, right? Have you guys ever done matrices that are not n by n, that are m by n, that are rectangular? You guys do that in linear algebra? Yes? Yeah? Awesome. What did you do with them? You solved what, with pseudo inverses? With Gaussian elimination? Okay. Oh, like an augmented matrix. Ah, it's boring. All right. Everybody, when they comes out, they always say that A is square. A does not have to be square. And actually, in most cases that you're going to be encountering in reality, A is not square. It's a lie. I'm sorry. Right? A being square is kind of like a convenient truth that people kind of like use to manipulate. And in a lot of cases, it is square. In general, it's not. I forgot to mention, if you do look up condition number, I saw some people with Wikipedia yesterday, which was my prompt, and I should revisit that one. Wikipedia talks about singular values. They don't talk about eigenvalues. Singular values are the generalization of eigenvalues to rectangular matrices, obviously. Because eigenvalues are so obvious and nobody has problems with those, singular value decomposition is the extension of, right? Singular values are eigenvalues for rectangular matrices. Don't worry about that. That's all you need. That's all we're going to cover for singular values. But you're going to keep seeing these crop up if you do look into like Wikipedia. And the Wikipedia articles are like, they're not kind of the metered information feeding that you're going to find in textbooks. Textbooks will still be talking about them as eigenvalues. Wikipedia and all like the online repositories are going to be calling them singular values. Wherever you see singular values, just replace that with eigenvalues. Hopefully that'll be clearer, right? They're calling them singular values. Okay. All right. Because we're interested in the dimensionality, we're not interested in the magnitude of these things. We want to know, like, how does this algorithm change if we give our linear system 10 unknowns or 100 unknowns or 1,000 unknowns? How much longer does the computer take to crunch through this thing? What that's going to give, in general, we're going to be able to approximate that. And we're going to have some expression, it's going to be some polynomial, right? So whereas n is the dimensionality of the problem, we're going to have n cubed, 14 n cubed plus 3n squared minus 2, right? All we're interested in, again, is the leading term there, the highest power of n. Because as n gets large, that's the one that dominates. If you guys did sorting algorithms, do you guys do sorting algorithms at this point, like computational science or anything? Okay. Sorting algorithms are all over big O notation and computational complexity. Quick sort, which was the fastest in my day, right, had, what was it, n log n? I think computational complexity, and right, that matters about how quickly you can do something as the number of those things changes. If you haven't done that, no worries. Okay. Typically, matrix multiplication between two matrices, n by n, row by column, row by column, row by column. Every time you do a row by a column, you're going to be doing what? N operations. Should I draw this? Would that help? I think that would help. Tomorrow might be a quick lecture. Do I say this? Wait a second. Do I really not go into that? Oof. Mike. All right. Say you have two matrices, right? I've got A, B, C, D, dot, 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 dot. I've got another matrix here. I've got, what should we call this? F, G, H, I, J, K, K, dot, 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 right? If I'm going to multiply these through, row times column, right? One operation, two operations, three operations. For n by n, every time I do one of those, I'm going to get n operations, right? How many times do I have to do that? Sure? N cubed total, right? Every time I do that, that takes n operations, but I have to do that for this element, the resulting matrix. I have to do that for this element, for this element, for this element, for this one, n, 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 n. That is the same dimension, n by n, and I have to do that n times n times n times n cubed. Plus some gobbledygook nobody cares about, plus times some constant nobody cares about. All we're interested in is as n goes to infinity, how that computational complexity increases. This is not the most efficient way to multiply two matrices. This is a massive numerical problem. Some dude managed to find a way to do this in order n 2.81, and it was lauded as a massive victory. Anyway, matrix vector is all over small things like video games, for example, and basically everything else ever done on a computer. So if you ever manage to shave off like 0.000001 in computational complexity of matrix vector, that's like Nobel Prize territory. Anyway, some common things. What if you add two matrices? This guy, 1. This guy, 2. This guy, 3. This guy, 4, 5, 6, 7, 8, 9. N squared. Everybody see that? Excellent. Matrix multiplication, standard algorithm. Matrix vector multiplication, when you have n times a vector, which is n, you calculate that out, it happens to be order n squared, right? If you ever get that down to like a lot below, I think the most efficient one is like 1.7 or something like that. Matrix inversion is terrible. Right? That's also n cubed, and that turns out to be a really terrible result. Calculating of the determinant. If you work through, I think it's like Kramer's recursive algorithm, it works out to be n cubed algorithms. Transpose is actually pretty simple, n squared matrix norm is squared too. You could be tempted to time this. And timing it, this is my signal that you should be paying attention, by the way. Some other guy like 2 years ago, he was talking about like, I think he was talking about problems with the UK nuclear subs, and they were talking about like delayed hydride fracture and things like that. And like he couldn't say certain things because it's the UK nuclear subs. So every once in a while in the presentation, it'd be like, and this phenomenon, and this phenomenon, and look over here, and look over here, right? And this was like, hey, pay attention and pitch me a project studying this, but not being allowed to say that. Anyway. Right? So this is me like, hey guys, pay attention because you just might come up with a question to it. If you use the timeit function, timeit is built into the, I think it's built into the IPython environment. You can time the amount of time that it takes to evaluate some function. you can use that. I'd like to ask that as a question, but we're out of time. You can use that as to quantify the efficiency of a certain operation. So in this case, we're generating two random matrices and we are multiplying them. Matrix multiplication. And then we're going to time it for different sizes of matrices. And what you see is when we increase, the first one is increasing n by a factor of 10, and we get roughly 1,000. Longer time, longer execution, right? This is microseconds, it's milliseconds, right? So you get 1,000 times longer function. When you double that, because it's n cubed, right? 2 to the power of 3 is 8, right? Not bad, actually. Difference between that and that is, yeah, I could see that as a function of 8, as a factor of 8, right? You do this again, what's that, 0.2, and you get up to 1.32. Is that a factor of 8? No, right? The reason why it's not is that the time at function is not just doing the operation. This is computer science territory. It's calculating the wall time of an operation. And the wall time involves the algorithm as well as whatever else the computer is doing in the background. So the computer is talking to you, it's moving stuff around the memory registers, right? It's doing all that stuff that gets baked into the time at function. That's why, like, if the computer is doing other stuff, this was evaluated on the GitHub servers, right? It's super busy. It's doing other stuff. Maybe it's a little bit busy with something else. It's not an exact function. It is not as good as the algorithmic computational complexity, but it's a very quick and easy surrogate, right? So by all means, use it, and you might be prompted to use it real soon. All right. Oh, I got 5 minutes. What are we doing tomorrow? LU decomposition matrix types. Yeah, I could do that tomorrow. Should we go through Gaussian elimination? We have 5 minutes. And what do you have questions so far? Yeah. I have absolutely no idea. I have absolutely no idea because it is, I suspect it uses the more efficient one. Because this is why you want to use packages. Because this 2.81 algorithm, for all the benefits it does, I have no idea how it works. Absolutely none. This is somebody who's been studying this stuff for 50 years and their lifetime achievement is 2.81. And it is a momentous achievement to be able to do that. I don't know, and to be frank, I don't care. You know, like this doesn't affect me as a human being very much, right? But the fact that they did it is fantastic, and I will celebrate them for that, right? Use the package. Don't write a matrix multiplication algorithm. It's not as good as the one that the guy wrote for like 50 years. It's numerically robust and all this other stuff. Any other questions? Okay. I'm going to try and slam through Gaussian elimination so it gives us a bit more breathing space tomorrow. I'm going to give you guys your first assignment tomorrow, by the way, and then you'll have Monday's lab time to work on it, but at least you'll have the weekend to kind of like think about it and have it cement in your mind a little bit. Okay. Gaussian elimination, you already know. That's the good news. You already do this. This is how you've been doing this substitution way of solving these equations. It is the formalized algorithmic way to do it. And I'm guessing you guys did that because you were just talking about the augmented matrix. Okay. What you do is, so returning to our original problem, right? You have 20 plus 50, 700, C plus T equals 20, and you solve, right? You rearrange this for substitution, you plug it in, and then you can solve like that. Everybody know that substitution? If not, go back. Okay, the numerical approach is a lot more algorithmic because we're going to go into like these larger systems, n by n. So we start off with the same thing. And what we're going to do is these line matrix operations. So we're going to take the second equation, multiply it by 20, and then we're going to have, and actually by negative 20, right? We're going to have 20C plus 50T is 700. And then that C plus T is equal to 20 becomes minus 20, minus 20, minus 400. Slap those two together, and now you've got this 30T is equal to 300. Okay? If you look And now at this point, when you've got like something times t is equal to something, that's trivial. That's the bottom level. You don't really need to go farther, although Gauss-Jordan would. Okay. When you do that, if you look at the matrices, what you're actually doing is looking like this. You've taken your 20, 50, 1, 1, and through this matrix operation, this line operation, you've transformed that into something, something, 0, something. And this 0 is the important part. This matrix is called an upper triangular matrix. And it's super useful because as soon as you have an upper triangular matrix, what you do is you do back substitution. 30 times t is equal to something, divide through, plug that guy into this one, and you can solve for everything. Once you solve for your upper triangular matrix, the rest of that solution becomes trivial. And it becomes easy. And that's actually what you're doing. That is the formalized method to what you're doing with your substitution algorithms. When you boil it down to a single variable, and then you start subbing that variable back in and go up and up and up. So upper triangular matrix have zeros below your main diagonal. We're not going to go into what that means for rectangular matrices, right? And an equation of this form, this should be a vector here, turns into blah, 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 blah. And what you would do if you're ever faced with this is say x4 is equal to b4 divided by u prime 4, 4. Substitute that into the next line. Substitute that, solve for this guy. Substitute these two values into the next line and back propagate it in order to solve your entire thing. Okay? Gaussian elimination does exactly that. You transform your original problem, ax is equal to b. If a problem is hard, even when a problem is not hard, you make it as simple as possible and then you solve it. That's the whole like decomposition thinking, right? You're going to transform ax is equal to b into this upper triangular x is equal to b primed, because in doing so, you also transform your vector here through the augmented matrix, right? And then you do the back substitution. I'm out of time. We're going to talk about the algorithm tomorrow. So where last we left off, we started talking about Gaussian elimination. How far did we get? We got to upper triangular matrices, right? Okay. So just as a reminder, you start off writing your equations in the matrix form, and then you go through and you do your row by row operation, right? You take the first one, you say, okay, I want to eliminate this c variable. What do I have to do? I have to do 20 times the lower equation, subtract those, and I get that. And when you look at the matrix equivalent, what you're doing is you're zeroing out these columns here, right? This type of matrix is called an upper triangular matrix. Everything is always with reference to the diagonal. The diagonal is probably like one of the most central concepts of the matrix. It's also pretty self-explanatory. It's the diagonal, right? Upper triangular is everything, including the diagonal, and up is populated. Everything below that diagonal is 0. We're going to see what lower triangular matrices are in a second. Okay. Blah, 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 blah. And then when you get into an equation of this form, this upper triangular form, this becomes trivial through back substitution. This one, you solve for that, you plug that into here, you solve for this, you plug those two into here, you solve for that, and you back propagate up. So Gaussian elimination is the process of transforming this system ax is equal to b. Sometimes it can be nasty, so you want to make it easier, and you do that by making it ux is equal to b primed. Okay? And that's through Gaussian elimination. Again, the way that you do that is you form this the augmented matrix by slapping one into the other one, and then you do these operations, exchanging two rows, results in flipping a sign, multiplying row A by a constant, right? Oh, sorry, this is the effect on. Sorry, no, this should be A bar. This should be the determinant of A. Not just the effect of A. So the nice thing about this, all these row operations, is they're not going to change your solution, right? Your solution doesn't care. That's why substitution works. Solution is independent of that. But your matrix properties are not. Okay? When you're doing these things, you actually end up changing the properties and the behavior of your determinant of the matrix being intimately related to the solvability, if you remember from the past couple lectures. So when you exchange two rows, you end up flipping the sign on A. This is general. You can work it out for 2D, 3D, but it's ND, right? If you multiply A by a constant, you end up multiplying the determinant by that constant, and you subtract two rows, and it doesn't change anything. And the nice thing about this is that we can take a matrix with a poor determinant, right? We talked about the value of the determinant right? The only real dangerous part is 0. That's one we want to avoid. If it's 0.00001, it's a very thin area on the enclosed trapezoid. We don't really worry about that because we can always scale it to be larger. How do we do that? Multiplying a row by a, and then we get something that's larger for all the good that it does us, which for direct algorithms is not very significant. For iterative algorithms, we'll see that it is significant, actually. And that's part of one of the things that we're going to be doing to these things. Okay, so this is a formalization of the steps. I don't really have time to go through all this, but these are the results, right? You got 20, 50, 700, 1, 120. That's our original equation. The original determinant is, right? Analytically, it's minus 30. Is this minus 30? No, but also yes, right? This is finite precision in case. Okay, the norm of A, this is the Frobenius norm, the Euclidean norm, Pythagorean is an extension of it. And the condition number, if you calculate it, by the way, calculating the condition number is super easy. NumPy, linalg, cond. Okay, so one of the reasons why I want to show you all these code snippets, so that when you look at the assignment, which is already open on A2L, and you look and you say, hey, he's asking for the condition number. How do I calculate that? Go look in the notes, and it says, this is how you calculate the condition number. Okay, I'm pretty sure you would actually also be able to just search it, and it would come up with cond. Yeah. Or Gemini or Google or any one of those wonderful tools. Okay, so that's the condition number. 100, 96, 97 is not bad. It's at least only, like 2 orders of magnitude, but it could be better. We want it to be 1. So what we're going to do is we're going to, well, in this case, all we're going to do is multiply through the bottom row by 20. That changes the determinant, as we said, because we're multiplying through by a scalar, right? Changes the norm a little bit, but the condition all of a sudden is much better, right? And all we've done is just multiply one of those equations by a constant. That's it. Obviously hasn't changed the solution, but already our numerical system is going to be behaving better. This is a form of diagonal scaling. It's in the preconditioner section. We're going to talk about it next week. It's the most trivial, I would say, of the preconditioners. Depending whether or not you consider diagonal dominance to be a preconditioner. I think probably some people would. Anyway. You do the subtraction, determinant hasn't changed, norm hasn't changed, condition number has changed, but I mean, this is peanuts, to be honest. Both of these numbers are blah, blah, blah. Effectively 6. Need more of this guy. Okay. So, the algorithm. There's a reason why I'm going to run through the algorithm. It factors into LU decomposition, which we're going to talk about next. Don't worry about making notes on this. If you don't know how to do Gaussian elimination, honestly, you could derive it. If you were ever asked to do it in the real world, you will never be asked to do it. Professor Mike says, so it shall be. Okay. Not just, by the way, I don't just mean in the class. I mean like ever. Okay. Gaussian elimination. We want to solve this system of equations. Now we're finally up to 3 by 3. Okay. What we do is we turn it into a matrix. Right? Just like wave your hand if I'm going too fast here. Okay. We get the augmented matrix. You slap on the solution onto the side. That's there. And now what you want to do is you choose the first equation as the pivot. Pivot is a bad word. Unfortunately, it's kind of duplicated. There's the pivot row, and then there's pivoting of the matrix. And unfortunately, the way it's organized is that now we're talking about pivot row. In about 5 minutes, we're going to be talking about a pivot matrix. So, and I apologize, they're actually fairly different concepts. Welcome to math. So what we do is we choose the first equation as the pivot, right? And we turn the second row, first element, to 0. That's our goal here. We want to eliminate that first element on this column here. On this row. To do so, all we have to do is multiply the first row by 0.5, negative 0.5. Right, depending on if you're doing plus or minus, and then subtract it from the second row, right? And all that does is it just zeroes out that, and we're going to keep track of this constant here. So just for the sake of this algorithm, again, you're not going to need to know how to do this. I'm just showing you how the algorithm is constructed. Okay, so this is your pivot equation. The first constant here for the second row, first element, we're going to use negative 0.5, right? And then we're going to do the same thing for the third row. We're going to go through, and this time we multiply the pivot by 2, and then subtract it, and we zero that out too. So all we've done is we've just taken that first equation and we've used that equation, we multiply it by constants, subtract out the other lines, and we just zero out this entire column, right? We're going to systematically create this triangular matrix, upper triangular matrix. Now, this part is good. This column is good. So we move on to the second row. Our second row is now the pivot, and we want to zero out this element in the third row. So what do? We multiply through by 4/5, subtract it, and now we've zeroed this out. Okay, and we're also keeping track of this 4/5 is negative 0.8. Elimination is now complete. We've now created this upper triangular matrix. And then the rest is trivial. We solve x3, blah, blah, x2 is therefore that, x1 is therefore that. Does that make sense, roughly? Everybody got the idea? Good. Okay, the complexity of it turns out to be the elimination phase, which is where we create the upper triangular matrix, is around n cubed over 3. Usually, again, if you're doing big O notation, you don't worry about the constant. Here we are going to, because it is kind of interesting. Well, we're just going to talk about it in a second, right? Therefore, the order of the algorithm is ON3, and the back substitution is ON2. So it seems like we've actually like increased this, right? We've made a more complicated thing because now we have to do both, but bear with me for a second. An obvious extension to doing this is to not bother with the back substitution phase, right? If you wanted, you've made the upper triangular. Now you just take the lowest row. That got people's attention, eh? There you go. If people are dropping off, I just do that and everybody's back in, right? Right? Obviously, if you propagate it down and you've zeroed out that lower triangular part, you can just reverse the procedure and zero out the upper triangular part, right? And then all you're left with, no, shouldn't be crass with those terms. Once you've zeroed out below the main diagonal, you can also zero out above this, the main diagonal. And while you're doing so, you actually end up with just ones. And this is trivial, right? Like, here is your answer. The system is solved. There's no further information necessary, right? The problem is the computational complexity. This is a case study in that. Gauss-Jordan elimination, the elimination phase takes n cubed over 2 in order to get to this matrix, which is now trivial, right? As compared to Gaussian elimination plus back substitution is n cubed over 3 plus the back substitution phase, which is n squared over 2, right? And that is always going to be a little bit less than Gauss-Jordan elimination. And it's like, it's a little bit of a squeak. Makes a difference, right? It's a difference. If you have a computer code, that's right, most of you guys have done COMSOL. If your COMSOL code was taking an hour, or you can make a little tweak and it would solve in 45 minutes, right? It's not peanuts. It's not going to be like the game changer in the world, but it's not peanuts. Okay. Gaussian elimination is very fundamental, but it's largely been surpassed by matrix decomposition. We're going to learn exactly what that means. It's been surpassed, and it's effectively obsolete to the point where it's not even implemented in most Python environments. NumPy, SciPy, none of these guys have Gaussian elimination. If you did want that, you would need to look up the SymPy. Sorry, SciPy is the scientific Python. NumPy is number Python, right? SymPy is the symbolic Python. If you were to use symbolic Python, they have the reduced row echelon form, right? RREF is the other kind of word for a matrix of this form. Sorry, I think this is row echelon, and reduced row echelon is when all these are ones, right? Not necessarily zeros up here, but if you really wanted to get that, you could get that through the SymPy RREF, right? And that's what you would get. Any questions on that? Yeah, sorry, that was an accident. Although effective. Okay, there's a big problem. The order of the rows in the matrix is arbitrary, right? If you're given a system of equations, it cannot matter, right, what order you write those equations when you're scribbling down on the paper. Obviously, it doesn't matter, right? So when you put it into the matrix, right, if you put it in like this will solve with Gaussian elimination. This will not. And the problem is that you've got this 0 right on your main diagonal right at the top, right? So your pivot row in this case, you can never multiply anything in order to cancel out this -1. And it's kind of a trivial thing, right? Like, obviously, the solution is... Who's got a solution? What do you do? If you've got a matrix like this and you want to solve it with Gaussian elimination, what do you have to do? Just switch 2 rows. That's it. Which is the other connotation of pivoting, unfortunately. Other people will call it permutation, but I want to at least show you guys that you got to be a little bit careful. Okay. Fortunately, swapping rows in matrix algebra is very easy. All you have to do is called the permutation matrix, and it's basically a row swap of the identity matrix. So it's super easy to show that the effect of this is just to take the first row, put it down, take the last row, put it up, and you're done. This is called the permutation matrix. You are going to encounter it either before Monday or on Monday. I'm telling you right now. Wouldn't it be nice if there were a generalized concept that would include the case of zeros being on the diagonal? Turns out there is. It's called diagonal dominance. In general, as a general statement, if the diagonal element is small compared to the other elements in that row, we're going to run into problems. Right? And the derivation for this is beyond the scope of this work. This is like 20-year research project, right? To work this out, they came up with diagonal dominance, and it's actually a super simple way to think about this. We can actually derive this a little bit by just, if we did have an epsilon here instead of 0, right? We go through the first pass, we end up with all these things, and like, look at this. As soon as epsilon gets close to 0, we're going to have this massive inflation because we're dividing by something close to 0, right? All of your numbers get big. Now you have big numbers that are in combination with small numbers, right? We know that's a recipe for disaster with round-off error. This is like it's not the full proof. This is just a very simple case where you can see like where the problems are going to come in and hit you. Okay. Thus, we don't want the diagonals to have zeros or small numbers, which kind of motivates this idea of diagonal dominance. It is defined to be, or it is said to be diagonally dominant if each diagonal is larger in absolute than the sum of all the other absolute elements of the row. Okay. So, which one is diagonal dominant? Obviously, right? Well, actually, no, not obvious. Okay. Who thinks A is diagonally dominant, right? So in diagonal dominant matrix, every single element on the diagonal is bigger, never mind all your signs, than the sum of all the other elements in that row. Who thinks it's A? Put up your hand. Who thinks it's B? Obviously, right? Obvious because you guys have all been in a class with a prof, and the answer is always B. Otherwise, it wouldn't be. Otherwise, it would be boring. This one is not, because 2 is not bigger than 4 plus 1, right? 1 is not bigger than 3 plus 1. Neither is 1 greater than 4 plus 2. Super easy to look at, right? This one is, and it's the same matrix. Your solution hasn't changed, but just by swapping these rows, you have effectively changed all of these, the behavior of this. Further, it can be shown that if a matrix is diagonally dominant, you shouldn't touch it. You will not be able to improve the conditioning of your matrix by row swapping if it is diagonally dominant. So you look at a matrix, you see what it looks like, and as long as that diagonal kind of like dominates the other elements in that row, then you're okay to proceed. In 1 second. Yeah, it minimizes it minimizes one form of round-off error. Nothing is eliminated. Nothing is minimized in general. It's just one patch in the ship. Yeah, and it's also very, very important for iterative methods. Again, we're going to talk about those next week. Question? Yeah. Everything is absolute value. You don't have to worry about that. It all comes down to, because what you're really concerned about is mixing magnitudes, right? When you have something like this and epsilon is small, it doesn't really matter if this is positive or negative. That 1 over epsilon here is going to be huge, and it's either going to be positive infinity or negative infinity, both of which are terrible. Yeah, and either way, you're going to wash out the 2. You're going to wash out your original matrix element here, which is where the round off kind of kicks in and everything goes to heck. Any other questions? Yeah. Yep. Oh no, the formal definition is that the absolute value of your diagonal is the sum of the absolute values of everything else. Yes, yeah. Okay, let's talk about what people actually do. This is not the way that people actually do this, by the way. I'll come back to that rant afterwards. Okay, we're making good time. This is good. Okay. Typically, you will never be solving ax is equal to b once. You will be solving ax is equal to b, then ax is equal to c, then ax is equal to d, then ax is equal to c. Whatever the next letter was, I think it went backwards there. Doesn't matter. We're going to be doing this for multiple b's. What is the most efficient way to do this? One way is actually to form this longer augmented matrix. You could actually just take all of your solution vectors, b1, 2, 3, 4, 5, 6, 7, just slap them onto the end of this matrix. And in that elimination phase, you're actually going to be solving everything like that. Seldom the case. Very seldom, are you going to get to the case where you have to have all this stuff solved all at once. You're going to know your solution vectors all at the same time. Typically, if you're doing this sort of thing, you're going to be doing some kind of iterative walk or something. And then you don't have the next solution vector until you've already solved the previous one. Okay. So what we want to do is make this solution process more efficient. And the way we do that is through matrix decomposition. I've got to say, this is kind of like the heart of the course, right? And that I clumsily alluded to that kind of on the title page, right? Like the whole name of this game is to take something that's complicated, like even a linear system, even a matrix. Matrices are ugly. So let's break them up into simpler matrices, right? Nonlinear equations are ugly. So let's break them up into linear equations. Partial differentials with nonlinear implicit time stepping is ugly. So let's break it up into upper diagonal linear systems, right? And it's all that art of breaking it down. If you guys have done, I guess you guys have done like some computer science at this point, like modularity, stack, version control, all this stuff, like error control, being able to maintain all this stuff, it kind of fits into the same structure. I mean, honestly, that's mathematics, right? This is how mathematics works. It's all kind of like propagation of the simple forward. Anyway. There are other reasons why we would want to use LU decomposition, and that has to do with parallelization and high performance computing. I'll come to that one in a minute. Okay, we've already seen the efficiency gain from this decomposition process, right? Because of back substitution. The upper diagonal is much more computationally efficient than and scalable than actually just trying to invert A directly, right? Because it solves an ON squared. Any square matrix can be decomposed into the product of a lower triangular and an upper triangular matrix. It's a general statement, mathematically proved. The magic then is what happens to this equation, right? You start off with AX is equal to B. That becomes LU X is equal to B. And now what we're going to do is we're going to solve that problem in 2 steps. The first step is we're going to solve for a temporary variable, y, and we're going to let y equal to this ux, right? So we cut off this part. This becomes y. Ly is equal to b. That's this guy. And then you do, should I turn off these lights? That'd be easier. And then you plug that in, and you solve this guy is equal to that one. Do you guys see how that works? All you do is you plug it in and then you just move it over. Better? Worse? Good. Okay. The nice thing is that this solves in ON squared times 2. Both the forward propagation, the backward propagation is the solution of the upper triangular matrix. Forward propagation turns out the forward substitution of the lower diagonal. In general, L and U are not unique. There are different L's and U's, and the one that you calculate and the one that you calculate won't necessarily be the same one, even though the product of your 2 matrices still recover A. returning to the previous example, we found that this matrix, when we did Gaussian elimination, this actually turned into the upper triangular matrix, right? We actually found the upper triangular matrix to this, but the lower triangular matrix is basically what we had to do to that B solution variable while we were doing that. And that turns out to be a collection of all those constants. So the first thing we had to do was multiply the first row by negative 0.5, second row by 2, third row by negative 0.8, slap some ones along your diagonal, and now you have your lower triangular matrix. Again, a lower triangular matrix, not the, because they're not unique. This was the way that these were originally constructed. Doing the Gaussian elimination gives you both U and L. L is kind of like baked into the algorithm while you're doing it by hand, but you can pull that out and you can recover it. Yeah. Put a pin in that one. No, sorry. Take the pin out. This equation, because this is triangular matrix, solves an ON squared. This one, because it's also triangular, also solves an ON squared. The problem is that decomposing it costs ON cubed. So there are reasons. It's not an obvious thing. I'll tell you why we do this. Yeah. Correct. All those, when I said like you take the first equation, the pivot equation, multiply by negative 0.5, right? That negative 0.5, that constant, becomes this element in your lower triangular matrix. And then the next one, for the next row, we had to do 2. And then to eliminate the last column there, we had to do negative 0.8. Anybody else? Okay. We can verify this, by the way. If you don't believe me, just plug in the original matrix. These are the L and the U, that we calculated with Gaussian elimination. And sure enough, yes, it does reconstruct it. Okay, let's check the package decomposition. Note the hands. Let's check the package. The assignment is out. LU decomposition in the packages doesn't just result in 2 matrices. It results in 3. Guess what the P is? Right? L and U, those are obvious. Guess what P is? There you go. That's why we covered it, right? P becomes this guy. And if you multiply all these guys together, PLU, then you recover the original matrix. Note the order. A is equal to PLU from this particular algorithm. Okay. The pivoting operations inside the LU package, NumPy's, is this NumPy or SciPy? I think it's NumPy. Nope, SciPy. Okay. The package implementation has internal pivoting. And if you continue along this way and you get into the industrial strength codes, PETC is a big one. I'm pretty sure there's even a console option actually that talks about row pivoting during your solution. This is like the super advanced 3-level deep settings that you would get into this sort of stuff. But it is there. You can play around with it. Some people even do even funnier things. They use other methods that are also related to this diagonal dominance and things like that. But we're not going to go there to that depth. Okay. Even though, because somebody jumped the gun, it's good, right? Even though L and U, the L and U solution phase cost ON squared, right? The decomposition Gaussian elimination, by which we calculated in the first place, costs ON cubed. So we've actually increased the load. This hasn't actually helped, but there are a number of reasons why it's preferred. First of all, the decomposition only has to happen once. So if you have, right, You guys were all paying attention in the class, right? This is my hey, pay attention, right? If you decompose your A matrix, PLU, that costs ON cubed. You solve for a particular system. Then you have to repeat the calculation because the engineer got something goofed and forgot a decimal point. You'd be surprised how often that happens. Oh, I have a great example. Oh, I'm going to finish this and then you guys are going to laugh and cry. Oh man. Okay, you'd be surprised how many like stupid mistakes get through. Oh, like lunar rover, was it the Mars rover that crashed because somebody forgot imperial units instead of centimeters or something? I've got an even better one, but okay. First of all, if we want to repeat this calculation for different p's, we've already done the factorization. Now we just need the application. And the application only costs ON squared for these guys, for the L and U solution, plus a little bit of row swap. Row swap is super trivial, and some addition in there, right? And you're done. So it is much faster for repeated operations. There are also parallelized algorithms, and this is kind of the pay dirt for distributed computer when we can speed up the wall time. So a lot of these textbooks, and one of the reasons why we now have like course notes on this instead of the textbooks, a lot of these textbooks were written before the days of massively parallelized computing. I'm pretty sure my phone has, I think, 2 or 4 cores. My computer has at least 2. I think the most cores that I've ever worked on was 512 at Argonne, but like people regularly go up to millions of cores. So if you're going to go into scientific computing in general, you're not going to be working on like console on your laptop, right? That's great as an engineer, absolutely. Computational multiphysics, hooray. But if you're actually going into like the hardcore scientific computing, Mateo, right? Like if we were doing this on like the Zerk hydride things on the much larger scale, we're going to need not just like 100,000 degrees of freedom, not just 100,000 by 100,000. We're going to need millions, right? And the nice thing is that you can split that up. And you can split that up into different computers, but that splitting up procedure is highly algorithm dependent. With Gaussian elimination, every single time, so the name of the game is that you have to distribute it. So I need to give part of my problem to you guys, another part to you guys, another part to you guys, another part to you guys. The more you guys have to talk to each other, the more things are related to the, what do you call it? The communication bandwidth between the cores, right? On top of your core, inside your CPU, everything happens fast. As soon as one CPU tries to talk to something else, God forbid you talk to the hard drive, never talk to the hard drive, right? All of a sudden your performance tanks. Saw your hand? Give me 1 second. The modern approach to LU decomposition is using advanced methods. There are 2. One is called supernode and frontal algorithms, and that distributes it among the different cores and then brings it back together. And you can get much better performance than vanilla ON cubed. That's the name of the game. That's why they're doing this sort of thing. Question? All we've talked about so far is solving linear systems, which requires a square matrix A. In general, that matrix does not have to be square. That goes into something called the pseudo-inverse. And I'm struggling I'm struggling to figure out when to introduce you guys to it, because we're going to need it with curve fitting. When you are solving, as a spoiler, an answer to your question, when you're solving a rectangular matrix like that, you need something called the pseudo-inverse, and that requires you to form a square matrix out of your rectangular matrix. That's kind of like the cheater answer to it. I think we're going to be talking about that in 2 weeks' time. In 3 weeks' time, I would love to hear you guys if you think that it would be better introduced in the linear system thing. I think if I introduce it right now, it's just too much, and like everything linear systems is just going to leak out one side while I try and cram something else in the other side. But let's talk again in a few weeks. So LU decomposition, is on one core. Now, LU decomposition can be handled in a few different ways. The most elementary of which is Gaussian elimination. And Gaussian elimination takes ON cubed on a single core. There are better ways, quantifiably better ways, that can do it in faster the N there relates to your system size. So if I could take something that was a system where N was 10, and I give you 5, and you 5, now you've got 5 cubed plus 5 cubed, which is dramatically better. I don't know what is that, 125 times 2, I guess, 250. I guess I do know, versus 10 cubed, which is 1,000, right? That's the name of the game with this distributed algorithm. The problem is that Gaussian elimination can't be split like that. Because at every time you're taking one line and you're propagating that to every other line. And that communication part sinks you. It destroys you. It means that you have to talk to them at every single time, and every single time everybody gets confused, blah, 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 blah. So the idea with these multifrontal algorithms is this, the 10 by 10 actually turns into something more like maybe 7 by 7 and 7 by 7. But even 7 cubed plus 7 cubed is less than 10 cubed. That's kind of the name of the game with this parallelization stuff. But like all these algorithms, like this is why I don't want you guys programming in your own Gaussian elimination, right? I had somebody come to me as a co-op who had a Gaussian elimination. I'm rambling. I'm running out of time, right? I said don't. Like we have packages. Okay. Direct solvers are your black box. I think in console we only ever use direct solvers, right? Mumps, Paradiso. Stop me if you recognize any of these terms. All of them were direct. There were a few more advanced ones, and we kind of relied on console's backing to handle that. They are the most robust for ill-conditioned systems. We're going to talk about, what else we can do with those ill-conditioned systems. But in general, if you have something that's kind of like on that borderline, you want a direct solver. They scale terribly, absolutely terribly. Ethan's fired, coming in late. Joking. Right? They scale terribly both in terms of size and parallelization, right? It's very difficult to do, but the benefit is that they're very robust. If your direct solver doesn't solve it, nothing else is going to. If you use them, and I think I repeated this in computational multiphysics, start small, work up to your large ones. Right? I think in the beginning, I scared everybody. I said, have your finger on like the power button to emergency exit, right? You don't want to get to the point where you're even talking to your hard drive. Then things get super slow and your computer gets bricked. Generally speaking, even if you try and parallelize, you will not see a speed up until you get to a larger number of nodes. Nodes is cores. Let's say it's not actually, but let's just consider them cores. I only saw the speed up after about like, I think 7 or 8. Then things started to ramp up. In the beginning, it actually got longer. And that longer is associated with the cores talking to each other. The payoff isn't there until you get to a certain system size. Some implementations are actually capable. The other benefit of the pseudo-inverse is that you can actually invert singular matrices, which is funny. And there's a lot of impact to that statement, right? Some systems, some implementations are smart enough to be able to do that and not even tell you. Now you've got a problem because you solved something that you really shouldn't have. You found a solution that isn't the solution that you think it is, right? Just be careful about that one. Sparse matrices, the next section, are your saving grace. Do your best to protect them, and hence the LU factorization. Oh, sorry. Yeah. You want to have sparse matrices. You want to have sparse matrices. All of scientific computing wants to have sparse matrices. The only excuse for not having sparse matrices is when you have to do something once and repeat it a million times. And that's actually spectral methods for partial differential equations. But that's another story. Okay, very quick story because I think it's hilarious. And then we're going to talk about matrix types, and I'm going to do the assignment quickly. Okay, there is, who heard of nuclear waste? Who's heard of disposal into like, what is it? I think it was a clay or something, right? Like it's not bentonite. They were talking about something else, right? What they wanted to do is put these spent fuel rods into like a canister and backfill it with inorganic material. And somebody wrote that down as put it into the canister, fill it, and then put in inorganic material. And the scientists wrote that, being careful about their terms. And then somebody reviewed it, and the technical writer got it, and the manager got it, and somewhere along the line, the packet in inorganic fuel or inorganic material became packet in organic material. Dun-na! You would be surprised how many stupid mistakes happen. And like the whole name of the game is trying to minimize your stupid mistakes. It happens in numerical methods. It happens in like organizational and like, have you guys talked about like the Challenger accident and stuff like you'd be surprised when this sort of crap comes up. I don't even remember how I got into that one, but it doesn't matter. That's a funny story. Okay, let's talk about matrix types. Slam through these guys. Zero matrix, obvious. Identity matrix, also obvious at this point. Yo. Oh yeah, shoot. I don't know. Yes. But so when you do Gaussian elimination, you take your original matrix A, and then you slap on that B vector to make your augmented matrix. And then you follow those procedures, and you're manipulating that B matrix at the same time. Oh, sorry, that B vector at the same time. Does that, right? So you've got your A, right? You've got da 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 da, and then what you do is you take that B, and you slap it onto here. And then you do your elimination, right? That eliminates this guy. This guy becomes a 0. This now becomes B primed, right? Now you do this guy, and this now becomes B triple primed or something like that. Just doing this, if you wanted to now change from B to B2, right? You would need to do that entire elimination phase again in order to get your solution. And that's wasteful because you already did it. So what LU decomposition does is it separates out the effectively, right? You separate out the elimination phase and what you did to the B vector. That's what the L matrix is. It's what you did to the B vector, right? And by separating that out, if you now get another B, then you just repeat that procedure, which is an LU system solve, right? To that B vector profit, because that's only n squared, order n squared. Anybody else? Okay. Matrix types. Identity, diagonal. We spoke about this. Interesting property. So A minus A is 0. Yep. AI is equal to A. I is the identity matrix is the ideal matrix because it is the 1 in your equation. Anything multiplied by a 1 is 1, is the original thing, right? If you could make your A matrix into the identity matrix by multiplying through by something like a preconditioner, right? If you could make that into your identity matrix, then the solution would be trivial. Because then you just have x is equal to 1, y is equal to 2, z is equal to 3, right? You just carry that right over. Okay, we've got a diagonals there. Interesting property there is that the inverse of a diagonal matrix is actually just the inverse of the diagonal elements. That's another nice thing that we're going to talk about with diagonal scaling. Upper triangular recovered, lower triangular recovered. Permutation matrix is one of these matrices where you end up swapping the rows. A nice thing about that is that the transpose is the inverse. Those two are actually related. Symmetric literally means everything on top of the diagonal is the same as below. And symmetric positive definite, we're going to talk about when we talk about conjugate gradient, iterative methods, has this nice property. It is effectively the, you can imagine that as a quadratic, for example. We'll talk about that one later. Sparsity. Sparsity is your friend. Embrace sparsity. Sparsity refers to the fraction of non-zero elements in a matrix. Okay, sparse matrix have significant fraction of those zeros, and that dramatically and drastically reduces the amount of storage and the computational requirements for these things. Typically, one has to store the entire matrix A. And A can be big. If you have a million variables, if B has dimension of 1 million, Your A matrix is going to be 1,000,000 by 1,000,000. And that's big, even for a computer. Just even storing that thing is nasty. If you have a lot of sparsity, you don't have to worry about the zeros. So there are entire data formats. I forget what they're called now. I think CSV. I have an example down there. Not CSV, that's comma separated values. CVS or something, right? That has the benefit of only storing, right? It indexes the non-zero values. And then you just assume everything else is zero. And if you have a sparsity pattern like this, come to it in a second, that has dramatic payoff. Okay. Fill in, when you're doing an algorithm, there's this phenomenon called fill in. And what that means is that during the computation, zeros become non-zeros. Remember when I made a big fuss about protecting your sparsity? Fill in bad. Fill in, make zero, non-zero, sparsity, tanks. You want to avoid it. Okay. One way that we can visualize all this is just by like printing out, making a picture of the matrix where every non-zero element is a black square. And when we do that, for a finite element method, like you guys have done, what you end up with is this. Anybody want to comment on this? What do we see? Somebody raise hands because we got to wrap this up. Yes, definitely symmetrical. Absolutely. Anybody else? What about the diagonal? Somebody in the back. One of you guys. Do you see the diagonal populated? Right. If you permuted this, if you swapped any of these rows around, it would not be diagonal along there. And remember, if sparsity is on the diagonal, you have a problem because that is never diagonally dominant. Right? You want the diagonal to be propagated, to be populated. Okay. Yeah. Banded matrices are a little bit of an extension. They can be described by a term bandwidth. That's the number of parallel bands, and they look like something like this. Okay? And these are actually very common, especially in finite difference methods, right? You have your main diagonal. You almost always have your main diagonal. If you don't have your main diagonal, you have a different problem. Okay? There are particular cases. That's something a little bit outside. But then what you want to note is how the diagonals above and below that are also populated. This is called a tri-diagonal matrix because you have 3 rows that are populated. Your main, your one up, and one down. And when you visualize that, right, looks pretty clear. Pentadiagonal is something that looks like that. And you can also have, oops, do I have an example of that? Yeah. And you can also have generalized cases, right? These are all banded matrices because they have these nice ordered arrangements. This is actually very common in finite difference. Finite element, not so much, is because of the way the triangles fit together when you're tessellating all this stuff. Finite difference, or if you were doing that on a rectangular grid, then you would also see this sort of structure. Very, very useful. There's also the notion of block matrices. Did you guys cover blocks in linear algebra? Okay. If not, if you look at this, you might already kind of see that up here is almost one distinct block where everything is filled in. Over here is actually an identity. This is an identity, and then it's actually the same thing as over here. So the idea is that you chunk this up and you break it into something like that. You can have a form for the inverse. You can invert a block diagonal matrix. This looks terrible. It looks nasty. But remember, every one of these submatrices A, instead of M being 6 by 6, A, B, C, and D are all 3 by 3. And B and C are the identity. And A and D are actually the same. So you invert one of them, you've inverted all of them, right? C and D we said were the identity, or sorry, B and C were the identity. That collapses a lot of this stuff. This is actually very common where you see this sort of things, especially in multiphysics. So you didn't see it in COMSOL. That was one of the things that was buried. It was talking about this. Does anybody ever come across the segregated mode? Or like the fully coupled versus segregated coupled? If you drilled into some of the solver settings, even though I warned you not to, what it's doing is it's solving something like this. It's called physics-informed preconditioners. If you're ever in Idaho, they'll be all hot about that. Right? It's a huge benefit if any of these submatrices are 0 or 1. Yeah. Okay. Block diagonal. Simple extension. The off-diagonal ones are 0. Right? What this actually means is that the inverse just collapses to be this. A inverse, D inverse, no problem. Let's look at matrix decompositions. That takes that. This is a different type of, this is called LDL decomposition. It takes that complexity. There's a reason why I'm talking about this. The symmetric one, symmetric positive definite, has this thing called Cholesky decomposition, right? In general, we have this matrix inverse formula where the inverse of A is related to the inverses of U and L, although not in the same order. You got to remember that one. Okay. I don't think I'm going to get to the assignment, actually, but this is very, very important. You could be tempted to store the inverse of A. By hand, if you're ever doing this, what you do is you calculate the inverse and then you multiply through. That is not the way that you do it in numerical methods. It is vastly more efficient, and I'll show you exactly why, to factor it and store the factors. And this is why. The inverse of a triangular matrix is triangular. Okay, so if we just take this and we do the inverse, then we're going to end up with another triangular matrix. The decomposition of a banded matrix is banded triangular, which is to say that, so this matrix, which is banded, right? When we decompose that, it is banded triangular. What that means is that the lower triangular portion in this case still has this set of diagonal lines. We haven't disrupted the sparsity. But there is one that is very bad for sparsity, right? Remember this fill-in idea. The inverse of a banded matrix is not banded, except for the diagonal. This is why you don't do this. If you take that, this is our nice banded matrix. Notice all the zeros. You invert it, and you end up with the black wall of death. Remember that I told you banded matrices are all over the place. Sparse matrices in general. Do I do that too? No. Sparse matrices, banded matrices are very common at this level. Later on, sparse matrices, doing the inversion, finding A inverse, obliterate your sparsity pattern. You get from something that is nice and clean and pretty and everybody likes to honestly the worst thing ever. Yeah, okay, so these are the functions that you can use. What else? These are different iterative algorithms. A lot of these ones we played around with is COMSOL, but you might see them out in the wild, right? And here's just some examples of how you would actually use this stuff. That's it for that. Did anybody manage to get the assignment off of A2L? Yes, does it work? Okay, but you at least managed to click on it, yeah? Okay. So when you click on it, when you click on that link, it should open up your own Google Colab, right? That particular version is locked. You're not going to mess around with that. You have to save your own copy, export it, and submit it. It's due next Thursday. Pardon me? Yes. Yeah. If you want to use a different environment, that's fine. Just convert it back to IPYNB. If you really don't need to, we can talk about it, but IPYNB is easier.